almost. But yeah, so let's start. This is the last session of the day. This is the last discussion of the day and of the meeting. So it will be, we'll talk about, actually, we have learned so much at this meeting that we will basically try to summarize it, and most important, try to think what we'll do for the incoming years. We have two communities, gravitational wave and supernova modelers, and plus the multi-messenger, and what we can do. So I prepared a few slides, and at first I thought that I will do like summary of like each subject, but with this amount of information, I will do a poor job. So we'll do all the brainstorming, but let me go first through these few slides and to initiate discussion. So as we had a nice lecture from Marianne about what will happen after 04. So basically we will have the next 05, and then hopefully A sharp, which can be probably it will call like 06. We'll have Virgo next, Kagra plus, possibly Australian detector. So a lot of good things. Then I tried to look on if we would ask a question, if we would have a galactic supernova for the last 10 years, would we have a chance to detect it? And it's pretty depressing, but this is the past. Future is better. So let me explain. So if you think about the detector coverage, for the last 10 years, we had 4 observing runs. And to detector case is like 25%, which includes two LIGO detectors and plus Virgo. Single detector was like 9%. So overall 30% coverage, which was better than I thought. And of course, the first 01 was much lower sensitivity than what we have now. Virgo also improved. Sky coverage, I just put like the number of 80%. But if we would have galactic supernova, our range is pretty limited. And because we are at the like 2/3 towards the end of the edge of the Milky Way, even if we have sensitivity of few kiloparsecs, it basically covers only a small fraction of Milky Way. And I look at the numbers from the LVK papers, and it ranges, depending on the model, from a fraction of a percent to maybe like 20, 50, 70%. So I just put the number 10% of like some models like in the middle. So this is even if we'll have galactic supernova a little bit further away. Yeah, first it's more likely that it will happen like further away versus closer. And also astronomically, in Milky Way, it's more likely that we'll have a light star of like less than 15 or 20 solar masses, and rather non-rotating. So taking all of that into account, the overall, if you have a galactic supernova, you have 1% chance, ballpark, of really seeing gravitational waves. So I want to ask a question: can we do better in the next 10 years? And some stuff we don't have under control. Like we cannot say like, you big star, explode. You are rotating fast, explode now. So we don't have that under control. So what do we have under control, and what as a community we can improve? And just list it, we have more detectors, say better coverage, and that's something hard to basically put it in number now. A little bit better sky coverage. We'll be a little bit more sensitive due to the hardware, and we have heard a lot about software. And I just want to say what Sergey said, which I'm in. Observers want to work with the observables. So I would like to this 1% to bring to higher number. So for me, this discussion is about we have all this discussion about improving the models, about improving the sensitivity, but in general, can we make much stronger? Is it possible to increase possibility of discovering supernova in the next 10 years? So just a reminder, we'll have a white paper. Everybody is welcome to contribute, to publish their own work in the proceedings. We won't have a Slack channel or something else. Like, we already created a Slack channel for the communication, but what is the thing that on the free version, your posts disappear after 3 months. And we want to continue a little bit more over 3 months. So that's something to think about, just how to have like better communication between us. And I just was thinking, should we have like more regular meetings post this symposium, one per month or one per few months, but to constantly stay in touch. Then this is our initial outline of the white paper. Basically, the motivation, what we have learned here, what is the progress in theory, in detection, in parameter estimation, our lessons learned, what do we have to do in the near future, what are the opportunities and action items. So this is something very, very rough, but that's something, given this whole volume of information that we have learned here, we will have to start like putting everything systematically together and think of how we should really organize it and what we should be the input. Then we have discussion just in a second. So this is the QR code. But before, I have some extra slides. We talked about the data and like a large volume of data and a lot of thank you for all this feedback that you want to share your data. But I just want to warn you that as an example of neutrino data, there's 200 gigabytes of data that you have, that then it is dumped into like small volume of like 5 gigabytes. But what I need, and this is just my personal need, is basically one number. What is the time of the collapse? So where we should basically start to look for gravitational waves. Then of course the light curve, that would be nice, but this is as for me, I just need this one number. So yeah, if you think about sharing the data, don't expect us to or me to analyze all of it. Just we need not much. We don't need much. Okay, so I would start with the discussion. We have the paddle made by Marco. So I would like to maybe let me have it so you can actually look at this. It's can somebody actually share it also on the WhatsApp so people have link? It's shared on the Zoom, but almost nobody here is on Zoom. So yeah, what do you think about the next 10 years? What significant progress we can expect? How to increase the chances of discovering of gravitational waves? What are the immediate needs? What are the immediate comments? Is the question actually asked correctly? So I would actually take it a few moments to actually start going through that. And this is right here. Maybe like 5 to 10 minutes. Do you all have the link? Yes, please. You did? Yes. We don't want to be that astronomer. Nice, nice. Oh, I cannot move it. Okay. Mhm.
Great. Do you want it? So maybe it's secretly going to play in but the conference they on the other side of us, they're like 3 hours flight. Oh. Maybe that's it. Lower. We have a brilliant crop. Can I ask a question while we're doing it?
To the microphone.
So I wonder about this thing. So if you ask me what we should do to make sure we detect a gravitational wave from core collapse supernova in the next 10 years, my answer is to keep the detectors on, right? Like just keep them on all the time. I don't even want 05 plus or whatever. I just want detectors to be on because now we cover most of the galaxy, right? And for me, if we just kept them on as they are now, it would be great. But yeah, I know. But so my question is, how motivated is the LVK to really try to keep the detectors on all the time? And what are the supernovae group within the LVK kind of saying to the larger, like what is your guys' opinion on this?
Do you want to? Okay. Yeah.
I think it's not a decision that we will get any say in, and that it will be mostly determined by money. Like if they don't have money for upgrades, maybe we'll have a longer 04 and it will be on. But I think everything is really uncertain at the moment. Like we don't even know if 05 is going to happen. So I don't know what the plan is. There is no plan, but I do know that I'll get no say in what the plan is.
Just to add that I'm getting old, and sooner or later I will need to have my knee replaced, my elbow replaced, and so on. So it's not possible to keep the detectors on all the time. They are aging. Yeah, but maintenance may require months.
It takes years.
Yeah, so this is an upgrade.
No, even maintenance takes years, because if you have to vent everything and change the mirrors and change the suspensions, you're not going to do it in one day. So it's not possible.
So we were discussing this Core Lab supernova signals in a pretty high frequency. Is there any signal at 0.1 hertz from Core Lab supernova? And and at what strain it would be produced? Because I did not hear anything about that. Maybe I missed it.
You probably within the microphone. Yeah, if this would be.
I just want to tell you a story about something what is happening,
Oh,
and
if you don't mind.
there is a proposal to NSF actually to fund a detector which can detect gravitational wave in the range like 0.1 hertz, 1 hertz in this region. And what is actually one of the biggest problem with LIGO? It's a multi-billion detector, okay? And it's very costly to run and operate. And we could not expect that it will be on all the time. So this is just the reality. To run detector which is 100% on, you need something like a telescope, which you can put it in your office and point to the window and then see something. And actually there is a project like that. It's based on optical comps. And it's a scale of this instrument. It's no, not like 10 kilometers or 40 kilometers. It's like the size of book maybe. Okay. And the detectable strain is order of 10 to the minus 20. So, and but the good thing about this is that to build such detector and operate, you don't need the whole collaboration. You need just a university group. And I think that universities, they would be delighted to have such detector. Because it's like you spend, I don't know, 10, $20 million, and then you have a detector which you can run just in the lab. And you can have many of them. And I wonder if it has any value for Core Lab supernova, just looking at the low frequency signals, because in this case, it's practical to run these detectors all the time. If like one detector is off, you can have not just 2, but you can have 10 of them. It's still way cheaper than LIGO. And this is just my question. If as I said, the strain amplitude is approximately 10 to the minus 20. 10 to the LIGO, for example, the strain sensitivity is approximately 10 to the minus 24, like few times to 10 to the minus 20. So it's like maybe 1,000 times less sensitive. But for example, such detector can be used to detect gravitational wave from binary dwarfs. We have a lot of them in our galaxy. And they produce a very significant strain. The only reason why LIGO cannot see them because it's just simply out of the band.
Right.
And if of course, if strains, basically these strains produced by supernova are way below, kind of smaller than 10 to the minus 20, then it would be hopeless.
Right, right. But generally speaking, I think, we and others have emphasized this in the low frequency spectrum, Coulter's PRL emphasizes that we should start paying attention to the low frequency spectrum because of the memory signature and what information the memory signature brings to us. And it starts low, it ramps up into the order 50 hertz band and then ramps down. So it starts very low to be quantified, but something near zero, and then it could level off at something near zero. And it also has a fairly significant duration because it's caused by the global expansion of the material and the global emission, aspherical emission of the neutrinos over, 10 seconds, for example, as long as a black hole doesn't form. So, I mean, without sitting down and looking at the details, it's hard to be more specific, but I would say there is a use case. I mean, this use case has already been brought up, for example, with the LISA team for that reason, because that's at the top end of their frequency band.
Depends on the models. To the microphone, please.
It depends on models. In our case, at 10 kiloparsecs at 0.1 hertz, you're looking at 10 to the minus 21, 10 to the minus 22. But our memory, they're shorter simulations. It's a little bit lower. If you look at some of the rapidly rotating models or some of the stuff that David and Princeton have done, you're getting strains that are thousands of times bigger than that in some cases. So this kind of low frequency desktop interferometer has a lot of use for low frequency core collapse gravitational waves.
Had the right instrument.
So my question to you then, do you have any noise curves for this? Because I would love to look at it in more detail. I mean, we could easily evaluate this if you have some sort of a way of...
There are some noise curves and
or some sensitivity curves.
I don't have it right now. Basically to share it with you, but this work is done by Steve Aikenberry. Steve Aikenberry,
Are there any papers on this?
Yes, there are papers, but just recently they submitted a proposal to NSF, and the numbers which I heard for this basically it was kind of justified to measure gravitational waves from binary dwarfs, white dwarfs. But if memory, has comparable signal, then it would be a good option.
Yeah, I guess we need much longer simulations to know exactly how low frequency it goes, because the duration of the simulation determines the lowest frequency resolution you can go down to, and we also don't know how high the amplitude is going to go. So I think all we can say now is that it's probably going to be really loud and have a good science case, but exactly how low frequency and how high amplitude it is, I don't know, maybe we'll tell you in the next meeting in 2 years or something.
Okay, it would be very useful if somebody could send me, some numbers which kind of we can trust regarding the strain amplitude at frequency band around 10 to the minus 1. And then it would be interesting to communicate with these people, because you're absolutely right saying that actually the main problem is that we don't have detectors working all the time. And we will not actually have any detectors working for the next few years. Okay. But on the other hand, if it's possible to measure this low frequency, to have a reasonable strain for low frequency gravitational waves from core collapse supernova, then this instrument, they kind of could be useful. And it's one extra justification.
It's
for this experiment.
Yeah, it's tied to the explosion physics, not the detailed, the engine physics, so to speak, but the actual explosion itself. And it's tied to the birth of the neutron star, because it's the neutrino emission over seconds that's what dominates the memory. So yeah, the science case is easy, and I was going to answer another.
I would maybe a little bit defer to going away from this low frequency and maybe focus on the high frequency that is kind of the most detectable, because yeah, that's an unclear place.
There's a question up there about computational expense of 3D models. I wonder if we could get people to answer that. Do you want to do that one?
Okay. Mhm.
All right, so is Olivia here? Yes, is that, there you are. Is this from you, Olivia? Yeah, yeah, the one, yeah, so state-of-the-art models, the best models to date that don't make approximations, you know, that have the complete physics and have sophisticated treatments of those of that physics. So there are some approximations, of course, require not only supercomputers, that's a broad term, but they require leadership class computers. So the Oak Ridge Leadership Computing Facility is the biggest, fastest machine on the planet. And our models run on that machine, and we can only run several models for in a year for part of the time of a supernova's evolution. So we can run several supernova second equivalents. So 3 models at 1 second, for example, or 1 model at 3 seconds. And we already have seen from all the presentations that explosions develop over over timescales as long as that or longer. So, without significant approximations, and you know, you have to run not only on a supercomputer but on a leadership class supercomputer. There are a lot of large computers in the world, but you know, ultimately the state of the art today requires the best machines on the planet, and that's not enough, not even close. So I'll tell you when I answer.
And I was wondering, what's the status of the Curriculum Supernova codes when it comes to GPU acceleration? Because we know that the resources available for the newest machine, most of it is going to transition towards GPU accelerators. And in the community such as the GRMHD community, MHD, when it comes to different sophisticated contexts, that kind of transition has been happening, is happening right now, and people are really gaining speed ups of a factor 15, let's say, relatively routinely. And I mean, that kind of impact, I mean, is huge, but I wonder where we are.
So I can speak for theirs. David, I know, can speak for his, et cetera, Chris. So I'll put it this way. You can even, I mean, to get significant time on the OLCF, you compete for that time through Insight. And the last I heard, it was 1 to 10 oversubscribed, and it's probably worse now. So the competition to get that time is beyond, you know, belief. You cannot get an allocation on that machine unless you run the lion's share of your simulations over a significant fraction of the entire machine, and largely use the GPUs to do it, because that's where the power comes from. It's all, as you said, it's all in GPUs. So and I didn't get a chance to really go into, aside from the applied mathematics challenge of developing a tool like this for our team or any team that's doing this. There's the challenge of optimizing these complex multi-physics codes for these heterogeneous architectures. And so we have, you know, we have a team of people that, you know, who can write CUDA like you and I are speaking right now. You know, they have a facility with CUDA to, you know, muster the GPUs. You know, that's, you're absolutely right. Without that, you cannot do these simulations, period. So, and I was thinking of something else, but I've forgotten now. But yeah, so that's a must. All right, it's a must.
Yeah, if I can add to the question, another related question, and I'd be interested in hearing from different group. When you showed the waveform from the Japanese group at the beginning, that you said that is the best currently from 2021, if I don't recall wrongly, that simulation, the paper contained 50 milliseconds. So what does it mean? We're going to get 20 papers to get 1 second of waveform? I know. I'm not saying that we should. I'm advocating for another presentation at this talk, but I'd be interested to have a chart from different groups. What is their opinion of what's going to happen in the next 10 years in terms of computational costs? Because that example alone is concerning me.
I think we pretty much all have charts of how fast we are now, because you usually have to put them in your grant proposals for your computer time.
So Michela, that's absolutely correct. And the bottom line is that, you know, the Kuroda simulation, I have very high regard for that. Obviously, I chose to single him out because the rest of the community needs to get to that point. And it's amazing that this younger man has done that. But yeah, I mean, you know, and probably if he's only run 50 milliseconds, either he's constrained by the machine he ran on, or by the fact, to Matteo's point, that it's not as optimized. And I know of other codes that, like Boltzmann codes, that are being developed that have still got, are not yet optimized for these architectures. And that's another, couple of years on average, 1 to 3 years of work to, once you have the, you have the code built, and you've debugged it and tested it and it works, then there's the business of optimizing it. But even given an optimized code, like Chimera, for example, with all of its physics and optimized code, and other codes that may be optimized, like Fornax, for example, David's code, that has been optimized by very knowledgeable people who know how to do that. That's what they do for a living. Even with that, again, without significant simplifications, we should not expect anytime soon, that is over the next 10 years, of each group doing this, pushing more than several models per year over a portion of the time. So over a 10-year period, we'll have dozens of models over a fraction of the time, or a few over, the full explosion time scale, where we can actually talk about explosion energies and things like that, memory, et cetera. That is models that are run out to, say, 5 seconds, for just to pick a number, right? As opposed to 1 or 2, 1.5. So it's just, that's the fact of life, So I think from our community, again, from the models that, are, let's refer to them as first principle models, I think what you're going to have to work with from our side is going to be, over the first, 1 or 2 seconds, and that's about it.
Maybe, actually I have 2 microphones. Maybe we can go to all these comments. Maybe let me quickly clarify this one number, because I was called explicitly. What do I mean for this one number? Imagine that the detectors are running 100%, coverage 100%. There's only 10% chance that we will detect the gravitational wave, just because the sensitivity is just limited. And if supernova happens on the other side of the galaxy, we will not reach it. 90% of the supernova will not reach it with the current instruments. So that's actually, that ties to Hakon. Do we want to keep it at low sensitivity, or we want to take it offline, improve, and then observe? Because we have to choose either. We cannot have both. Yeah. Okay, so
Can we do the one about the stellar models? It says, how can we convince the stellar physics community to work on how to evolve massive stars in a realistic way up to the end?
So, I mean, they are working on this. There's a meeting that's, I think, every other year called Stellar Hydro Days, where they are modeling stars in 3D. They're comparing their results. They're trying to improve them. They're trying to come up with new ways of doing, then recipes, because you do that, then you have to come up with a recipe that you put into your stellar evolution code so that you can model these early stages. So Marco was saying you have to get it at these early stages because that affects the final phase, and that's critical. So they are looking, they know what they need to do. Well, okay, they know some steps that they can do, and they're doing it, but this is not going to be a quick thing. The Stellar Hydro Days I was looking at, when I had last gone to it, it was in the early, like 2010, right? So they've been working on trying to get better for over 10 years. Not, I have been around for a while, not as long as some people though. But yeah, so they've been really working on trying to improve them, but there's a lot of work for them to do, and it's almost harder. It's harder than you think because they have to run time implicit in the end. When they go to the 1D code, it has to be time implicit. So whatever recipe they're getting that's having to capture this convective phase, unless you're just doing the silicon layer, when you go back into the star, you have to do it time implicit. So that's where the recipes get hard. I think it's going to be an iterative thing. They do some models, they plug it into the 1D code, they compare to observations, they say that's not working, they go back to the models and go back and forth. So I think it's still decades away to getting better, realistic stellar models. I think the real thing now is we know they're not good enough and they have to do something better, but it's going to take decades to get to the place that we really want it to be.
And just to add to what Chris said, because we were discussing this with Marco Limongi when he was here, who is our stellar evolution rep. Two things. One, as Marco showed, as Chris just said, that we've paid attention to the silicon burning stage, the very last stage, because we can actually, with a burning network, you can actually do that evolution within the supernova code. So great, but the idea is, as Marco emphasized, there are these earlier phases. So as we discussed with Marco, let's, can we develop a plan to push backward? Because the idea of having, as Chris was saying, a soup to nuts 3D stellar evolution model from, a protostellar phase through, to collapse, I mean, that's going to take decades. But if we start to back up from late stage and then investigate as we do back up what impacts there are on the outcomes, that will already be helpful. The other thing is we can already, as was done in pioneering work by Sean Couch, and Christian Ott, where they went in and they perturbed the core by hand in some way, right? And demonstrated that the outcomes could be changed qualitatively, like explosion versus failure. And so we can continue that kind of work in 3D as well to explore the impacts across models. But so there are two approaches here that are taking important steps within our community, and as Chris said, the stellar evolution community is working on this. But you sort of have to think in their case, as Chris said, like we were talking about in our case, we've been working on this problem for 60 years. Now the progress has not been linear; it's been exponential. The last 10 years, has brought far more than the previous 50. And I think that will happen in the stellar evolution community as well.
So we have a question about simulating black holes, like the first one on the left. Anybody would like to comment on that?
Maybe read the question out as well.
So this thing of
to
if we
the
can simulate the black holes properly, and there are people
Yeah.
doing this. There are actually people doing this, and all you need is you need to have this singularity tracking, and you need to sit down and you need to do it. It's hard to do. It's complicated. It's expensive, and you normally then sacrifice the neutrino transport or other things, and that's what people haven't want to do it. So they want to push the transport. But I am aware of a couple of people who are doing this now, and I really look forward to those results. So that this is happening. So it's ongoing.
With gravitational wave signals.
Yeah.
I look forward to seeing that then.
Okay.
Well, since now there are people from every community, let's say there is a signal of a supernova. I guess first it's gonna be the gravitational waves. So what's gonna happen? Like, let's say starting from Jade and Marco. So what's the protocol? I guess if it's something, what's the time scale that you will know it's a supernova? And then what's then the afterwards? So if you get the signal, you will see it first. Then there will be neutrinos, and then
Define
Ah,
signal, only GW plus neutrino.
no, I said so. What's the time scale of all of these to put it all together? Let's say that it happens today. So how is it happening? Because in my mind, it's really multi-messy as you described it. So let's say it happens today. I guess the first ones will be gravitational waves, neutrinos.
Right, but we're not going to know that. It's going to be the neutrinos. And so then snooze there'll be an alert, from snooze, and then the neutrino community will mobilize quickly. We, as Marco and I were discussing this, the community, I know the snooze folks, and we're involved here, and we need to make sure that the connections between the snooze network and the gravitational wave network are what they need to be. Yeah. But one thing we mentioned last night, just to give you an example, I don't know if Tobias is still here, but he reminded me of something really important, and Marco was very happily surprised. If Betelgeuse goes supernova, it's close enough that we'll see a few neutrinos, not many, a few in super K from pre-collapse neutrinos. So we will know before, we will have warning, pre-collapse warning. And then, as Marco said, things can really get locked in there, and we can, to speak to some other questions up there, be very prepared. So, but that's of course Betelgeuse, that's pretty close. But in any event, I think it'll be neutrinos and then coordination with gravitational wave network. The electromagnetic folks are going to, there'll be time, but
Yeah, I mean, they're already tied. So the electromagnetic people are already tied to the SNU. I mean, they've been doing this for kilonova already, so they're already tied on that end. What they are working on right now is they have lots of facilities. How do they utilize all of those facilities in the best possible way? And that's what this meeting in October will probably do, is we have a galactic supernova go off. When do we need to get JWST on it? Because that's going to require, if you need infrared early, that's moving mountains with JWST. So you have to actually, but if it's once in a, maybe not even once in a JWST lifetime, you could probably get them to do it. So there's going to be, they need to organize what should they be observing and when. But that, I think the fact that they know how to get notified right away, they've already solved.
I just double checked the number with Sergey. The median latency of an unmodeled burst signal online for LIGO is 30 seconds, 1 minute. Let's say 1 minute. You will know in 1 minute if there is
A loud one. If it's a quiet one, it'll take us much longer.
well, if it's significant, it will be released, right?
But get the precursor, like Betelgeuse, we get the precursor neutrinos, we'll get those before the gravitational wave signal. And
Yeah,
the reason I
is
was mentioned, making sure the communications happen is I was surprised to learn, and I'm not sure this is true, but Super K is not a participant in snooze. So if Super K will be the facility that sees these precursor neutrinos. And if they're not part of snooze, of course, somebody in snooze will know. And then, as Jade said, we'll connect with the gravitational wave community. But that's not efficient enough. We want to make sure that there's some kind of direct line.
Well, but we put out alerts SNEWS will put out alerts. It will be up to the electromagnetic astronomers to follow it up, right? I mean, just yeah, put it on your phone, get the alert, and if something happens, I mean,
They actually do, they have wide field telescopes, those go first.
yeah.
And so, because that way they can cover the error bars in the local
I mean,
station.
they did that with 170817,
Yeah.
right?
They go through
I
that.
mean,
Best is to go public as soon as possible and to let people get organized, because this is what happened with the BNS and it worked well. But I'm worried about the fact that for the Super K is not in news. And if Super K is the only one seeing something, I think, wait, no, and I understood they won't make any public announcement before publishing. That's what I understood from discussion years ago, and I don't know the situation if things have changed, but that should be a concern for us.
Yeah, because if they make alerts public, or even we could sign an MOU with them, and then we could put their, but if we need one and they won't share otherwise, then maybe that's something we should look into so that we get their alerts in low latency into our database. Another thing I wanted to add is that if you have do a search for a binary black hole or neutron star, and it's low significance, normally you wouldn't send out a public alert. But if Fermi sends out an alert and that goes into our GraceDB database, and then it's coincidence with a low significant gravitational wave trigger, then it gets labeled as high priority, and we look at it and we send out the alert. So I wonder if we need to do the same thing for gravitational wave burst signals that go into our database, like if they're low significance, but they're also coincidence with something from snooze or whatever,
So
then
maybe I
we
can
should
make-
elevate them to higher significance.
Yeah, I have a microphone. So let me make a correction. The rate of sending public alerts is 2 per hour. And only those that go below 1 per, I think, year for burst, then they go on your phone, then they are sent. But you have like thousands of like low significance triggers already in the database. So this is sent right away. So even if you don't get alert, you can go back to the database right away and look at it. And there is an infrastructure to look together with snooze alert and together with some electromagnetic. So this is all in place right now.
So how do we know if they're coincident? Does like Raven or something look for?
I think the window is like 10, 50 seconds, 60 seconds, or yeah, there's like pretty large window. Yeah, I don't remember the exact number, but the window is pretty large for the electromagnetic, and I think for snooze too.
But is it Raven that does that?
It's Raven.
Okay.
Yeah. Mm-hmm.
Just if I may change the subject, I'd like to address the really important question from observant stray dog. How difficult is it to put aside the politics and try to construct a real MMA community for a reasonable amount of time during the next 10 years? So I'm going to focus my answer to, an MMA community focused on core collapse supernovae. You're seeing it happen here in real time. That's one of the motivations for this meeting. As you have seen during the week, we've had representatives from the neutrino community, from the electromagnetic community, from the gravitational wave community. This meeting was, an important step in building this community. And I think, obviously, everyone knows we couldn't possibly get rid of all the politics in 1 week, but I think there's been some progress, some inroads, and some thawing here. And we'll, obviously are going to, from this meeting, as Marek will, discuss, as Marek discussed, we're going to develop a white paper, and that white paper, will be put on the archive for community, broader community to see. We'll be taking that white paper to the funding agencies, et cetera, et cetera. We'll be doing a focus issue. We hope to host we hope that this is the first in a series of symposia. And so the idea is, we've started something, we don't intend to stop. And I think it takes time to build friendships and trust that are the bedrock that underpin scientific collaborations. So that's a wonderful question. Thank you for bringing that up.
Yeah, I just wanted to add a follow-up on that. I think what we are doing is going to be important also for another range of things, in the sense that the LSE is already planning to morph into this IGWN. So the train will leave, but which direction will go is not maybe exactly determined. And I think, at least I can talk for some of my colleagues in the US, there is a certain degree of uncertainty of what's going to happen to the funding during this transition. And so having a plan that tries to protect those that work from, make sure that the funding agency understands the need to keep supporting this kind of research, especially in the overlap, I think it's going to be very useful if we can also help, if we can, in that direction.
I don't want to be the party pooper, but do you think NSF will gladly fund a field that has 1% chance of detecting something in this climate? I mean, unbiased opinion, right? Try put the NSF director shoe.
Well, I first of all, I think that someone could say, if we keep the interferometer as they are on, I know that 1%, I think we shouldn't discuss that openly, because it makes things look worse than they should be.
I think this is the place to.
Yeah, because I mean, we go to 1%. Someone could say, well, we can pump them up if we have a galactic supernova and we keep the interferometer on as they are now, and it goes up to 50%. Because we can catch roughly 50% of the model if we have an instrument that are up this way. So if we decide to bring it down, is because we want to voluntarily improve the performance, continue to reach the design sensitivity. The other reason why I think we can try to negotiate with the funding agency is that the deep nature of research is try to detect and what we have not already detected. And in my mind, Corcola supernovae are like the Higgs boson for CERN, is something that we know it exists. The point is to do the hard work to get closer and closer. And we're not going to get closer and closer if you don't put the work to keep improving the situation.
I can reply for sure. First of all, there is a difference with the Higgs boson because you can make it in the lab. The supernova, you cannot make it. But what I was saying is something that I heard in NSF panels from colleagues, right? Don't fund this, it's not high priority. They will never detect anything. So doing a good PR, I think it's important also.
Before 2015, everyone said we were never going to detect gravitational waves from binary black holes either. And everyone, the whole community did.
May I add a comment? to this?
Yeah, Andy has a question.
No, it was just a comment related to this. So I was the one who asked if there is a plan to avoid time gaps of gravitational wave detectors. And the short answer was no, there is no plan. And it is related to money and there is nothing we can do about it. So I wanted to say that I think scientists have a saying. Otherwise, for instance, after the discovery of Higgs boson, CERN should have closed, right? I mean, there has not been a huge discovery after that. And still there are a lot of fundings for this. So it's really important the scientists would,
Yeah.
okay. But it is important, the role of scientists. I mean, if you're acting pessimistic, of course, it wouldn't look promising, so.
Yeah, it's not about plan, it's about the reality.
Marco, I
course,
think
but-
there's some baby steps that are there along the way. Like we do have some collapses, rapidly rotating that, maybe the signal will go out and we can detect it to the Virgo cluster. So the first step, I mean, it's not like we have to say we need the galactic one or it's nothing. And that's how I think we need to sell this is our first step is we're gonna rule out some of the models or if we get a detection, then we rule them in, but we can, if there's a non-detection, that still teaches us something for things that go out to Virgo. So if we can sell it as we have again, it's a step-by-step, kind of how CERN did it, then you have something that we can say it's not like we're waiting for that galactic supernova. We're actually doing a step-by-step process.
Yeah, but we have to be careful.
Yeah.
Convey this message, be positive, right?
Yeah, that's right. We have to be able to say.
Marianne's next.
Mhm.
Yeah, I want to make a comment about that. There are ways to sell. If you say that you want to fund billions dollar project to discover one event, you're not credible. But if you're saying that you're going to understand how heavy elements are generated, to understand how all these high energy phenomena are produced, and so on, meaning we need to open the scope of our research. If we focus only on discovering the one event, I don't think we will succeed.
My comment was actually in the spirit of Marianne's. I'm thinking, Chris, of some of the things you said this week. But let me first go back and say to Michele that I'm glad you raised this point because that's an interesting question about, sort of whether in this white paper we just sort of think about, the science, right, the accomplishments, the needs, and steps along those lines, or whether we kind of take that next step with an eye toward sustaining funding. I think that's something we probably should do that, but that's something we're going to have to think about carefully. Yeah. But I'm glad you raised that because I don't know that we initially were thinking along those lines, but of course we're just going to get it started and everyone's going to contribute and all of these good ideas will come and in the end it'll be what it is. But Chris was saying that one of the things that's really important, and he can speak to this personally at Los Alamos in leadership positions he's had there, is that on the modeling side, and I think this is also true on the analytics side for the same reasons. On the modeling side, what we are training the next generation of modelers that will go on and do, to Marianne's point, that will have a significant presence and impact in other disciplines. Fusion research, for example, stockpile stewardship, but and at Los Alamos, astrophysicists have been among those that Chris has hired and have been part of these broader enterprises because of the overlapping physics and skill set. And so that can be part of the story. I think Marianne's point is really true, that the broader this looks, but real, the better.
Yeah, so there's a comment that astrophysics is the gateway drug into physics. And I think this particular topic is one of the best examples of that, where almost everything that's being done in gravitational wave detection, from the detector advancements, the analysis of the data, which is often difficult to do, and the modeling, all are getting people into and learning these skills that then are useful for a broad range of topics that Congress can get behind. So I think there we have a really strong case. So I agree with Tony on that.
Yeah, thank you. If I can add another comment, I think there are a lot of good point coming out. Definitely we have to be very careful what we say, as Marco said, and there is a difference between what we discuss internally. Say, okay, these are important issue we need to understand, and then what we put in a document that we use to communicate what we want to have as first round of goals. I think it's also important to talk about, I don't know, baby steps along the way. But if I wanted to add another thing along having secondary goals regarding the comment that Marianne said, I know CERN, I know has been banking for decades on the byproducts of the research, internet, I know vacuum technology, and even in recent years, I know has been one of the reasons why I know the funding has not stopped completely. I know Chris was talking about, I know, what if we could reach the Virgo cluster? Most likely hardware development to do that would require to produce the most powerful and stable cavities ever. And I know and some of these things could have implication in the future for other fields in terms of laser technology. I'm not saying that we should mention any of these things. And I know my opinion is that we ponder 10 things and then we choose strategically the 3 that should go in the document, but pondering doesn't hurt, and I think it helps in the long run.
Just go ahead, Jay. You were going to speak?
No, you go ahead.
Yeah, I was just going to say, just as a practical matter on these wonderful points that Michele is raising in this discussion, one of the benefits of having collected it in one room for 1 week, you know, the best in the world, the most expert people in the world across the major areas involved, is that we are very well positioned now to begin to craft such a document in such a case. And so I think, and this week is providing really a great you know kickoff for that activity.
So the rate is based on us trusting our gravitational wave amplitudes from our simulations. And I don't think that I do trust the amplitudes from our simulations. I trust the features like the high frequency mode and the call bounce and whatever. But I don't even think that we agree much on amplitude between different simulation codes. I think it's unlikely that you can detect supernovae in LIGO out to really large megaparsec because we would have seen them already. But once we get to the next generation detectors, a small change in amplitude is going to make a massive difference to the rates. And I don't really believe we've got the amplitude right yet, or that we even have some of the waveforms are even missing features, which is going to contribute. So I would like your opinions on that.
I'll jump in because I mean that's the point of this activity. I think as you know, we have made efforts in the past to organize the community for precisely these reasons. You know, to sort of have quantitative comparisons and checks and to come to some quantitative consensus on things like and issues like this and anything like that is going to matter. And so I think that's going to be part of what we start here and go forward. I mean, that's a very important part of organizing, say the modeling side, but then given that, as you know far better than I on, what are the implications then on the detection side and parameter estimation side, and we can do this together.
So actually, following up, I have a question. Let's say a little bit fantasy, but to guide the discussion. Let's say there is on the table $100 million, and you can choose only one. You can put it only on one basket. Would you put it on the models to get to know better the amplitudes? Go to stellar evolution to get 3D progenitor stars, or put the detector to cover the whole galaxy? Where would you put the money?
I think you probably I think if you want to build a better detector, you might have to add some zeros onto that number.
That, without shedding any blood here, at least to start to answer that a little bit. So first of all, the theorists come cheap, okay? So we don't need the $100 million in that sense, right? The real money is in the supercomputing time, but that's not something, you know, that just gets paid for out of other pockets. So we can assume that the leadership class machines will be there and we're going to compete for time and say we get the time. Then the amount of funding for, you know, for theorists is significantly less than the amount of money for facilities, you know, that we're talking about, right? So I think we don't necessarily, the choice isn't necessarily an equal choice, if you 100 million here or 100 million there. But certainly, you know, we can definitely advance the modeling in a very significant way. You know, if we had 10 million of that $100 million, with 10 million of that $100 million, if I had that, if we, the modelers, had that as a team, we could really make a lot of progress with that. So
would it be enough to get to know the amplitudes like pretty accurately? Or this would be like just a step that, oh, we are still unsure. Yeah.
I feel like I'm going to lose my badge now, but I would 100% put it on the detectors. I mean, because when you have a detection, you have the answer. Like that's like we do modeling because we cannot have a detection. Like this is but at the same time, I would gladly take the 10 million. So, you know.
In 45 minutes, it was, we need the models.
We do need the models. We need to understand the models.
We have a recording of that.
I mean, we need the models to maybe interpret, but I mean, the models, we need the detection to have something to interpret.
Yeah, I think a 90-10 split is, you know, optimal, right?
I mean, I wouldn't say no to $100 million either.
Pay tuition. And to answer your question, Dave, about, you know, if we had the $10 million, and maybe it was Marek, you know, would we get to the point where, you know, the amplitudes agreed? Now, I think the models with $10 million, you know, put in a focused effort to really advance the models in a center-like activity. It doesn't have to be spatially located, but, you know, center-like activity. You know, I think the models would advance significantly. I think the quality of the output would advance significantly. What the comparisons would look like at that point, I think it's difficult to say, but I think we would be, generally speaking, in much better shape. Of course, remember, there's still other uncertainties, right? So even if the models all agree on the amplitude for one of the progenitors, you know, the amplitudes might not be right because of the uncertainties in the equation of state physics or the neutrino opacities or the progenitor uncertainties, right? So I don't think we will ever, in the near term, in what's reasonable for us to think about and plan for, ever get to the point where a question like that, you know, will we have the amplitudes per se dead on, will ever happen? What, you know, it can happen. So even if we you know, eliminate the agreement, the disagreement, we still won't know if that amplitude is necessarily the one that we'll see. So then, therefore, if that's the case, then if there's some disagreement across the groups with sophisticated models, it's comparable. In other words, it's not necessary to necessarily have this, you know, with 100% accuracy. We won't be able to have that.
Now, Michele.
And just to add as a comment to that, I know, quoting Sean Couch, supernova could be like snowflakes, meaning that it's not one amplitude for the same progenitor. You could have different amplitudes. So we could trust our models or our modelers in this case, but know, it doesn't mean that we have the certainty of what certain range of masses will produce in terms of amplitude, because it might vary depending on the detail of the turbulence in that moment.
I mean, it's definitely going to vary, right? I always try to explain this to people because people ask me all the time, like, how far away can you see a supernova as if they're all exactly the same? And then I have to say, like, if it's a 9 solar mass star with no rotation, no magnetic fields, it's not going to have a lot of gravitational wave energy. But if it's a 40 solar mass star with rapid rotation and strong magnetic fields, then you're going to see it way, way further away. And I think this is something that's not understood by the community. They want like a standard candle, like they have the 1.4 solar mass binary neutron star merger. And there's not a supernova equivalent of that.
We're dealing with a stochastic phenomenon, as Michele just indicated, so, but there is already a lot of agreement, right, across the models. I mean, a lot of the spectrograms and the strains that we saw all week long from different groups across many models now with different equations of state, et cetera, all look the same. Now, as I demonstrated this, I'm not sure we know what happens before 100 milliseconds, but certainly I think we have a pretty darn good idea at this point what happens after that.
Maybe we can go to some of the questions. I was just looking at can information on neutron star equation of state given by the future neutron star merger, multi-mass merger detection, help in constraining PNS properties?
Definitely.
Nice.
Information from that end, will definitely help. So
It helps they're both really hot, right?
yeah, right. I mean, initially, as excellent point, Jade, because during a merger they'll heat up first of all, and then of course cool down, and the hypermassive neutron star for a period will cool down and ultimately become a black hole. The parameters the key parameters that I referred to earlier, ultimately it's all what underpins this is the nucleon interaction, and we're going to get a lot of information on that from neutron star mergers.
If I can ask you to extend your answer, do you think it could help enough to determine the needed mass to form a black hole inside a supernova?
Yeah, I mean, that's a tall order, but it would definitely get us a lot closer.
So maybe there's others Mark, actually, citizen science. So actually, that's, I think, a nice point, because how to engage outside of our community, right? Maybe do you want to talk
Marco,
about
are you going to turn us all into a neutrino detector?
Marco?
Well, actually, it came to me. It came to me a couple of minutes ago when we were discussing about outreach. Any plans with your codes and your models to do citizen science and outsource some of your simulations to, I don't know even if it's possible, right? But for in the LVK, we did it for glitch, noise classification. People doing pulsars did it. And
The problem is that with the simulations, we can outsource the plots, but can't outsource the management vector. So that's really close. You have to really be the integration
but even for parts of the simulations or
Post-processing,
sure, but not running the simulation.
But I think processing.
Yeah.
Good citizen science.
because well
processing, taking the simulation data from a leadership class computing run, and doing everything we've been doing, you know, analysis of the gravitational wave strains and modal analyses and all of that. And in fact, it's one of the vehicles, you know, I use to engage undergraduates in my program. Yeah, I mean, we have like a little army of undergraduates that have been working, you know, yeah. Yeah. Yeah, we have a 15-year-old prodigy who already understands general relativity better than my graduate students. And we have a 16-year-old prodigy. We have several undergrads, and these guys are forgetting there's been a stream of undergraduates who've you know, worked on this, you know, before their time. So.
Because you know, you could hit two fabulous pigeons with one stone, right? You get some computing power, and you do outreach, and you engage the public, and you get a good grant probably also, because in that
you can't, you have to be careful now how you say this, right? And you know, I don't want to get political here. But yes, yeah, no, that's citizen science is awesome, and it as Chris was saying too, it's definitely possible. Post processing, certainly even within the institution that one works in, you know, having students come from different departments, so they're citizens, right? But they happen to be at the university, but it can be broadened like we are doing now. We have 2 high schoolers that, you know, one's in Oregon, and one's in Tennessee.
Yeah, but I was thinking going beyond that, right? Really doing a Zooniverse project or something like that.
Yeah. No, excellent idea, Mark.
By the way, I just like very quick comment. We need like a more searchable movies of your simulations, because I'm trying to like find it. It's like hard. That's like nice selling, I think.
I have a little bit of a teasing question for Marco, since I know you have a background in theoretical physics, Marco Cavaglia. And since I know you have a background in our core theoretical physics, how did string theories got funded in the last few years? They're waiting for the outside.
I'll answer with a question. It's what's has highest probability, finding a supernova or discovering strings?
If you want me to hold one up here and I can help.
Well, I was thinking maybe you do what you want to do your end of conference speech now.
I think Michael is only. Oh, yeah, Michael, we need a joke.
Oh, so we have still 5 minutes. We have still 5 minutes.
Yeah.
So maybe before that, I want to ask
Explosion of the end.
Yeah.
Yeah, 5 minutes first though.
So I want to ask just a question. Given in our galaxy, we expect supernova from something that is like 50 solar masses and lower. Why to bother modeling 40 solar masses stars? If you want to focus on that.
Sorry, David. Let's should go over these.
David?
Oh, he got it.
Thank you. Yes.
Yeah.
Yeah, so we have a model of a 60, and when you say 60, you don't think of a particular mass profile, you think of an index for a density profile, because each group at each year may have different profiles. But a 60 that's more like a Wolf-Rayet star, has a large mass loss, leaves behind the strong gravitational signature. We also did a 100 solar mass star that we got from Woosley. I'm not sure if it's the same Z100 that was talked about earlier. And this one is pulsational apparent stability supernova. And there's a shock revival, but it fails and forms a black hole. But during that period of time, you would expect to have a signature, a high frequency signature, because of the turbulent accretion in the first half of a second.
Okay, but yeah, like the question is not about like the models. It's like why to do these models?
I mean, they do exist, right? It's just that we think the stars that explode follow like the IMF distribution. So there's more at lower masses than there is at higher masses. So the lower masses have more probability of occurring, but you do get supernovae at high masses as well. And we want to understand those too.
Right. But if you want to focus on detecting gravitational waves, that would be like if you want to keep a focus.
But that's a big if,
that
right?
would,
Like that is a big if. We care about many other things than detecting gravitational waves. So that's
okay.
my
That's important point.
Yeah. No.
Because,
That's my reason for doing other models.
Mm-hmm.
Yeah, and I think, Marek, I understand. I mean, there's going to be far more gravitational wave energy produced by, a 40 solar mass object. But I mean, we have to hedge our bets because, as Jade said, the IMF is telling us to put our chips in a different place. So we have to do them all. I mean, and we're not going to be able to do them all. I mean, just as an example, this wasn't discussed here. There'll be a preprint put out on the archive, later this summer. But we have models that are very, very close in progenitor mass and behave very, very differently. So the point is that some of the stellar evolution groups, although the models are 1D, I mean, there are increments in some catalogs. There are increments in solar masses of 1/100th of a solar mass. So there's really it never ends, right? In terms of running models, and they can differ quite a bit depending on the stellar structure. And stellar structure is not, necessarily a monotonic function. Or as simple as that connection is as simple as we'd like to think with progenitor mass.
There's a question that says, can Tony tell us what his mentor Galileo thought about supernovae?
To get me in trouble.
Yeah. Just because he made a comment about it, high school students throwing, charm at it.
Actually, you have a question from Olivia.
Hey, Olivia.
Gonna answer. So I think like it was like this is like more of a question from the previous question on why should we focus on stars over 50 solar masses as progenitors? And I understand a lot of people talk about Betelgeuse blowing up and that being the next big star. What about Eta Carina? I don't know. That star could blow up, and I think that thing's like, who knows? It's like some people say it's up to 120 solar masses, and it's incredibly unstable. It probably won't, but like, I don't know.
So I guess the simple answer, Olivia, is that we shouldn't focus in a particular stellar mass range. We really have to spread it out, and that's hard because, like, just from a practical computing standpoint, if our group has to only choose 3 or 4 models for the year, we have a choice, for example, of continuing models from the previous year so we can run them longer, but that means one less model of a different progenitor or whatever characteristic is hard, but we have to continue, and that's the benefit of multiple groups too, because everybody's, the models sometimes overlap, which is good for comparison, but they often do not, which means we're getting as a international group of models, we're getting more representation across the different masses. But Eta Carinae is going to be a different beast anyway in the end.
Okay, maybe we can cut it because we are at 6:30, and unless it's like a very, very quick question or comment.
There was one here, if we could have one last quick
Okay,
question.
just yeah, super quickly.
Yeah, just a quick question. So
I wanted to take this advice from anybody. So if suppose I want to write a grant proposal tomorrow based on Core Collab Supernova, and I need to compete with other astronomical proposals, how should I convince the committee that this is going to be the next big thing?
Personally, in mine, I
That-
put like a backup plan.
That is not, it's a great question. We probably have many answers to that.
Yeah.
A lot of advice. Maybe we can chat about it offline. I think that'd be great. We all have experience with this, you see, and that's why we're hesitant to even start that discussion.